Right, and the second part will be when we add disorder to such a model, and then we believe that we have found the long-sought random singlet phase in 2 dimensions. Okay, so let me give a little bit of background and context. So this is sort of outgrowths of work we have been doing for a long time on deconfined criticality, and luckily Ashwin already talked about that, so I don't need to spend too much time. But basically it's the quantum phase transition in 2 dimensions between the Nell state and the valence bond solid. And you know, some of the pioneers are of course here. So the main point here, at least from my perspective, is that this transition is generically continuous, which violates one of the Landau rules. Normally one would expect the first order transition if there's no intervening phase or coexistence between them. And of course there's some important role of topological defects here in the field theory formulation, that they are dangerously irrelevant. So one can, in the field theory, one don't have to consider defects exactly at the critical point. Now, okay, so to test this scenario, which has been quite controversial, we have been using this so-called JQ model, which is an extension of the Heisenberg model. So if you look at this singlet projector, the Heisenberg model is really minus singlet projectors on all bonds on the lattice. So now what we do with these Q terms, as we call them, is products of singlet projectors. And you can imagine that that will favor this kind of columnar valence bond solid. It's not completely clear, and there's not really any limit where you can solve this model or anything, but it sort of at least seems promising that you would be able to destroy the Nell order and get a valence bond solid. I mean, before this model, people talked about mainly frustrated models in this context, and we know that those are hard to study, you know, in some unbiased way. But this model actually doesn't have a sign problem, so this is just with combining these two. Doesn't have a sign problem in quantum Monte Carlo, so we can actually study very large systems, and indeed it has a Nell to VBS transition, and it appears to be continuous. I should probably say that it's still a little bit controversial because we see some unusual behaviors. But in any case, this is definitely what we call a designer Hamiltonian to study valence bond solid physics. Actually, since I'm in France, maybe I should say valence bond crystal, but anyway, there are different opinions of you know, what one should call that kind of state. And this kind of transition. So whatever it is, we can study it with this model. So what we have been focusing a lot on lately is basically there's some anomalous scaling properties seen here, and it's not completely understood yet, but I think we made some progress, at least in this paper here. This actually illustrates spin-ons. I will talk about that a bit more later. Okay, but now I will not really talk about this story, but what I will talk about is going to be at least building on this kind of model, and there will be some relationships to this deconfined critical point as well. Okay, so the first project is on this first order transition, so that's going to be in the context also of one of these JQ model with some modification. So this is done with 2 of my students at BU. So this work actually started with an experimental motivation. So recently in this material, which is the Shastri-Sutherland material, which I'm sure all of you know, a so-called Placket singlet solid was discovered. So motivated by that, we also wanted to study a Placket singlet state instead of, you know, this columnar valence bond solid. So we decided to design some JQ model to basically get that kind of phase. So I will talk about that and some simulation results, and then we got some quite strange looking results, and we are trying to interpret those, and it seems like there's emergent O4 symmetry, even though the transition appears to be quite clearly first order, so that seems unusual. Okay, so the experiment, so this is this paper from last summer. It's a neutron scattering experiment. So if we look at this Shastri-Sutherland material, so this is some animation that I stole from the web. I have no idea who made it first, maybe one of you, who knows. But you know, one of them is basically a layer of this material, and then you can deform it into this Shastre-Sutherland lattice, the two couplings, Heisenberg couplings on the green and red bonds. So what is believed, well, it's known, of course, that this model has this kind of bond singlet phase if these red couplings are sufficiently large. And then, of course, if those red couplings are absent, we have just Snell order. And in between, we believe that there's a Placket solid state where singlets form on half of these bonds with the Plaquettes with the bonds. At least that's what the experimentalists claim. Now, so what they did here is, you see there's one pressure here where, so when you change the pressure, you change the relative strength of these couplings, apparently. So they have one point here where they claim that some new mode appears, and they interpret that as coming from this Plaquette singlet solid. Okay, then they have some other points here. They have calculated or measured some gaps and so on, and they also have measured the TC to antiferromagnetism. And they suggest here that this transition between the Plaquette singlet solid and the Snell order could be a deconfined quantum critical point. Okay, so that,
sorry.
Yep.
Can you say a few words about the experimental evidence for this Placket?
Well,
just this new mode.
Right. So yeah, I don't want to spend too much time on it because it would take too long. But basically, they see a new mode that they don't see here. Some new, relatively low energy excitation, which they claim is from this one.
Neutrons?
Yeah, with neutrons. Yeah, this is from PSI, an experiment from PSI. Okay, so let's look at the Shastre-Sutherland model. So we have these two couplings, and okay, so there are many calculations, of course, for this model. I think the best one to show evidence of a Plaquette singlet solid is this work by Corbos and Frederick Miller a few years ago. So they did a tensor network calculation, and they even put the boundaries here quite precisely. So you see here you have these strong singlets here. So you have broken basically a twofold symmetry here. And what?
Picture from the experimental one, right?
Yeah, that's a good point. I didn't want to get into that, but yeah. So they claim that the strong plaquettes are there, and the experiment actually claims that the strong plaquettes are here. But I would say their calculation is a bit simple. I mean, they basically look at a single plaquette or two plaquettes or something like that. I don't think it's so convincing in the experiment what it should be. So but of course the material is not necessarily exactly the model. So who knows? In any case, they in this calculation they saw that it's actually a weak first order transition between these states. Okay, so that's what motivated us. Of course, it would be nice to do more calculations for this model. But okay, in quantum Monte Carlo we have sign problems, and other methods are okay. In spite of the fact that they got pretty good results, I don't think they could really study the phase transition very carefully. So we decided to just design a model that has these two phases, and then we could maybe say something about the phase transition. Well, they already said it's weakly first order, but we still want to look at it. So then we designed a JQ model, which is basically the same as before, but we put the Q terms only on let's say the black checkerboards. So on the same plaquettes where you have the diagonal bonds here, we put the Q terms instead. And again, the Q term is just a product of two singlet projectors. So it's two like that and like that, both added, so that you don't break any additional symmetries by hand here. And then we can tune this ratio Q over J. So then we wanted to see what do we really get a Plaquette singlet solid phase, and what kind of phase transition. So it's of course not still clear that we will get this symmetry broken phase and that the ground state is twofold degenerate and so on, because this kind of interaction is also completely consistent actually with the columnar phase, and of course it's not even clear that we will get out of the null phase at all with this model. So let me talk about how we detect bond or plaquette order in simulations without really going into details about the simulations, but just what kind of quantities we look at. So we need some order parameters for the dx and dy columnar order. So it's just measuring the bond strength, if you will, with the kind of modulation that we expect in a columnar phase. So this kind of order could also appear in this checkerboard model that I just discussed. But now I will just show some results for the standard JQ model, where we have the Q term on all plaquettes. So what we basically can do in simulations, we can, in a given configuration that we generate, and we actually do, we do in this case here, project a Monte Carlo in the valence bond basis. So it's very easy to actually measure these dx and dy. So we get some numbers from all configurations, and we can construct this histogram, which is not really a physical observable, but it's still something that tells us about the symmetry of the state that we get. So now I show some results for the JQ3 model, where we have these 3 singlet projectors multiplied by each other in addition to the Heisenberg terms. And these are some old results. So basically, if the system is, well, so in all cases here, if this is the extreme case where there's no J coupling at all, so it's the maximally ordered valence bond solid you can get, you see that we have this 4-fold symmetry here. So that corresponds to having columns vertically or horizontally, and they can be shifted up or down, so we get the 4-fold degeneracy. So if the system size is bigger, these blobs become smaller and sharper as the relative fluctuations of these order parameters goes down. So this is clearly an indication of a columnar state here. How about the JQ2 model? Well, it turns out that in the JQ2 model, even though there is a VBS phase, it's never very strongly ordered. So it means that in some sense we are always pretty close to the critical point. And we see this emergent U1 symmetry that is predicted within the deconfined quantum criticality scenario. So instead of these 4 blobs here, even when we set J to 0, it looks like a completely circular distribution. But note that it's a ring, so the distribution has some radius, which is basically the magnitude of the order parameter, but the angle has not been decided yet. So as Ashwin explained before lunch, you can associate an angle with the VBS order parameter. You can characterize it by a complex number. Okay, this is just to illustrate the fact that the simulations here are pretty slow. So if we go to a big system, it takes a very long time even to build up this whole distribution. So this is just because the simulation didn't run long enough. If it run long enough, it will cover everything. So to really analyze these, we can just look at the probability distribution as a function of the angle. And then we see for different system sizes, we do actually see this modulation. Here we use actually all symmetries that we can to make it possible to actually do that, even for this case here. So you see as the system size grows, these minimas and maximas become sharper. So even in this case, it is a columnar VBS. But we wouldn't need to go to really big systems to see this very clear 4 blobs here. So this is an example of an emergent symmetry, right? Yep.
J equal to 0?
Yes, so this is for J equals 0. Exactly, so when we move towards the critical point, the radius of this thing shrinks, and it just becomes a blob in the middle. So we, yeah.
Sorry, it looks like you have a horizontal.
Okay, so this is just some anomaly of the way to make the graph. Yeah, I use some very primitive tools to make these graphs. So yeah, so that's not real actually. Yeah, thanks. Okay, so yeah, let me say a few words about emergent symmetries. So Well, this is not necessary in this audience, but of course an emergent symmetry means that we have some symmetry that is not apparent in the Hamiltonian, but it emerges on large length scales. So this was an example here in this JQ3 model. If we look at these distributions deep inside the VBS for a fixed system size, we can see these 4 blobs, but if we go closer to the critical point, it looks like a U1 symmetric distribution. So here we can say that there's emergent U1 symmetry as we approach the critical point. And there's some length scale associated with that, meaning if we go to bigger systems here, we would also see 4 blobs, but there's some long length scale required before we can see that.
Then do you really say that it's emergent, or I mean, it seems to be still?
Okay, it's emergent as you approach the critical point. So as you go to the critical point, that length scale goes to infinity.
Okay, so but is that conclusive, or you?
Well, okay.
It could be much larger. Than
Yeah,
this.
of course. You know, like always when we do numerics, no matter how hard we work, somebody will always say, well, could it be if you go to 10 times larger systems, this all breaks down? So it means we are screwed, right? No matter what we do, you know, it's worthless, right? So we can only, you know, say up to, you know, the system size.
The reason why I
Yeah.
ask is because you showed this in the JQ2 model.
Right.
You showed the similar plot, but then when you plotted actually the minimi, we saw sort of.
That's right, but that was not at the critical point, right? So at any
Yeah, of course, yeah.
any point away from the critical point, there will be some system size at which the symmetry goes away, right? But the point is that as you go closer to the critical point, that length scale should diverge.
I somehow thought that you were talking about the critical point. And then
Yeah. No, so no, this is not the critical point because here, you know, there's a finite radius here. Right.
Oh, I see.
Yeah. Yeah, no, it can be confusing if you haven't seen it before, I know. Although you have even seen it before, but
Yeah,
still
yeah.
confusing, I know.
So I can do it.
So yeah, so we can definitely discuss more. Anyway, so this emergent U1 symmetry was, of course, you know, some important aspect of deconfined criticality from the beginning, but more later on, people suggested, you know, people in this audience here suggested that there could be even higher emergent symmetries, like in the SU2 spin systems, for example, in the JQ model, there could be emergent SO5 symmetry, which basically would mean that this, you know, U1, emergent U1 of the VBS combines with the O3 symmetry of the Nell order to form an SO5. And if we look at a planar, you know, XY-like spin system, it could be O4 symmetric. So this has been suggested in particular in this paper, and this paper was looking at some numerical evidence of that in the context of O4. Okay, so emergent symmetries have also been talked about a little bit at weak first order transitions, in particular in this paper here. So basically you can imagine that if you are close to a critical point which has such higher symmetry, but you are at a region where the transition is first order, but you are close to that critical point, then if you are really very close, that higher symmetry would affect even the system at the first order transition. So that has been suggested. So then you could ask, well, how close do you have to be? How weakly first order do you have to be to see any signs of that? And of course that could be characterized by some exponent, if you will. But there's nothing really concretely known about that. Okay. So let me get back to this model where we, you know, discovered something which seems to connect to what I just discussed about emergent symmetries. So let's now analyze the kind of singlet order we get in this checkerboard JQ model. Okay, so this kind of lattice and interaction is also compatible with a fourfold degenerate columnar VBS. You can very nicely make columns here. There's no problem to make 4 equivalent columnar pattern, but it's also compatible with a Placket singlet solid, which you can make in 2 different ways. So you could form strong singlets on these and weak singlets on those, or vice versa. So if this happens, then you break this twofold symmetry in the thermodynamic limit. So to check that, again, we use the same columnar order parameter as before initially. And then we collect the histogram in simulations. And now we see something quite different from before. Namely, we have only 2 blobs, so that seems to support the twofold degeneracy. And also the angle is shifted. It's not at the 90-degree angles anymore. And that's because we are now measuring columnar order. And if we have Placket order, a Placket is like a resonating Placket. So this, it's like singlets horizontally or vertically. So on average, in such a state, half the bonds are vertical and half are horizontal, so we would get both dx and dy order at the same time. So this very clearly shows that it's that kind of state. And these are some couplings pretty close to the critical point that we will find, or the transition point that we will find in between them. So G is the coupling ratio, J over Q. Okay, so let's talk about the phase transition. Again, we are detecting this kind of icing type order. So again, now I define my order parameters. You can actually measure these orders in many different ways. So now we did a different kind of simulation to really analyze the transition. So then it was more efficient just to measure the Z component of the antiferromagnetic order. And we construct some order parameter that can detect the difference between strong and weak plaquettes here. So we just take the product actually of Z components of the spins on all these plaquettes. Well, all the Q plaquettes. And then, okay, so maybe I didn't measure this phase is just the normal staggered phase, and this is just the phase which will be plus on, let's say, these blue circles and minus on the white squares. So if we take the squares of these order parameters, we can study those in the simulations. Now what I want to show here is something that is quite nice, the Binder cumulants. So those are ratios of the 4th and 2nd ordered second power squared of the order parameter with some coefficients such that if we have an antiferromagnetic order but no Placket order, this US will go to 1 and UP will go to 0 as the system size goes to infinity, and the opposite in the Placket singlet phase. So eventually we should get 2 step functions, and the steps should be at the same point if there's a single transition. So this is what we seem to find. So if we just focus on these red dots, this is the Placket cumulant for the biggest size we studied, in this case L equals 96. So you see it's almost a step function, and the rounding is of course due to finite size, and if we do smaller sizes there's more rounding. And this other order parameter, for what I call US here, it's an opposite step. And now what we do to really analyze the transition, we look at these Binder cumulants, and we analyze crossing points. So for example, the crossing point between these 2 order parameters, that's one useful quantity that can tell us where the critical point happens. And also we can analyze the slope of this quantity at the crossing points. We can also look at crossing points for the same quantity but 2 different sizes. For example, 48 and 96, they cross each other somewhere here in that case, and we can analyze that. So we do all kinds of things with these crossing points to try to calculate critical exponents and so on. Well, if we have a continuous transition, it can also tell us if it's a first order. Now, one thing, if you are used to these things. Normally at the first order transition, the binder cumulant has a negative dip. I will talk about that and give an example of that later. And that has to do with the coexistence at the first order transition. You can set up some simple scenarios of coexistence, and they will also always tell you that these cumulants will get some negative dips. But here, and that should typically happen, close to the step. But we see nothing like that here. So that may indicate at first sight that this is a continuous transition. Okay, let me show some other results. So this is again the same figure basically. This is looking at crossing points of these cumulants for different system sizes. The black ones is for crossing points between the different quantities for the same size, and the other ones are for different system sizes and same quantity. And you see that they flow to some value of G that should be the transition point. Okay, so this graph here is an important one. This shows the magnitude squared of, so the square of the order parameter at the crossing points, so at L, 2L crossing points. And you see that those actually don't go to 0. So if we have a critical point, of course the order parameter should decay to 0 with some power law as a function of the system size, but it doesn't do that. So we have both order parameters scaling to what appears to be clearly finite non-zero values.
Should I view them as very small?
Actually, yeah, it looks like they are small, but actually they are not, because this is the square of the order parameter. So if you take the square root and furthermore account for the fact that we have only measured one component here, then you should multiply that by 3. So in the end, this is actually something like 1/4 of the maximal value that it could possibly take. So it's actually not so small. Yeah. And then we can also, so that really, there's no question, this is a first order transition. Now we can also analyze the slopes of these binder cumulants, and one can easily show at a continuous transition that if you take the ratio of slopes for two different system sizes, L and BL, then that goes to the inverse of the correlation length exponent nu. And in this case, we can define two such exponents for the spin and Placket order. Of course, now we already know that this is a first order transition, but actually in finite size scaling, also nu has a value. But the thing is, it normally, let's say in a classical transition, one of a nu goes to the dimensionality of the system. In this case, you may think, well, maybe the dimensionality is d+1, so it should go to 3. Actually, you can see here that for these two cases, it goes to values larger than 3 apparently, and we think that has to do with the fact that this is the dynamic exponent is not 1 if we have this first order transition where you have these gapless excitations, so that's probably why it goes to even larger values. But in any case, this is definitely not consistent with a continuous transition, as we already knew from these results here. Okay, so as Cenk pointed out or asked, these values are actually not that small. So one could say that this first order transition is moderately, strongly first order. It's not really a weak first order transition. So then normally we would expect to have some pretty significant negative peaks there. So then we have to ask, why are there no negative binder peaks? So let me just show you what we get at a conventional first order transition in terms of those binder peaks. So several years ago with my then postdoc Arnab Sen, who is now a professor in Kolkata in India, we looked at the so-called staircase JQ3 model, where these singlet projectors are not lined up in a columnar way, but as a staircase like that. So then you will get this kind of valence bond solid. And here you don't have those local Placket fluctuations that allow you to rotate essentially continuously the VBS order parameter from horizontal to vertical, for example. You only have two of the, or you still have four of these, but they cannot be locally fluctuating to each other. So in this case, you know, we definitely expected not deconfined criticality, and then, you know, first order transition would be the most natural scenario, and this is what we found. So here's the bin accumulant for the magnetic order parameter, and you can see that we have those strong dips here. So this peak here should actually diverge as the system volume at the first order transition, and this is what it basically does here. And this reflects coexistence. I will not really explain exactly why, but it's actually pretty easy to see. But let me just show you some histograms illustrating coexistence of the two order parameters. So here I basically go as a function of Q3 at 3 different points and very close to where this negative dip happens. So let's first look at this one actually. So here you see 4 blobs for dx and dy. So that means that this is in a 4-fold VBS state now. But you see a little dim feature in the middle here as well. And if you go even closer to the peak, you see basically that dim feature becomes a real strong peak as well. And if you go further in this direction here, that peak takes over. So there's transfer of weight between these peaks, and that's really what coexistence is. When you go across the transition very quickly, you go from the VBS to the Nell order, but they coexist at some point in between. So here you see no, well, it's just coexistence in the expected way. And you see those negative peaks, which, you know, if you compute the bin accumulants from distributions like that, you will find that you have these negative peaks when you have the coexistence. Okay, but we don't see that in this checkerboard JQ model at all. There are no negative peaks, but it's first order. So how come? What's going on here? Okay, so then we were thinking, what do we know of any other case where such things happen? And actually it happens in some very simple context. If you just think of classical ON models, then as a function of temperature we have a transition between a paramagnet and something where you break the ON symmetry. So now if we look below TC, and you, well, I should have put a figure here, let me just, so this is T here. We have some critical point here. But now I want to put another parameter here, delta. So delta will be, so let's say we take just the Heisenberg model, the O3 model. I can put a delta in front of one of the components here. So then as I change delta, if delta is larger than 1, the transition will be Ising-like. Right? I'm not sure how this goes, maybe like that. It will be Ising-like, here it will be XY-like, and of course here you have the higher symmetry, O3. So when you cross this transition a little bit below TC or anywhere below TC, but let's say we are close to the critical temperature, then the symmetry of your ground state changes. So of course we may or may not call this a phase transition. I mean, it's like a first order phase transition, but there's also some aspect of a continuous transition here. If we think about it as a quantum model instead, and this is some parameter G that tunes us the quantum critical point, then on this side you have a gapped excitation spectrum, right? And the gap vanishes continuously as you go to delta equals 1. So it also has some flavor of continuous transition, but of course what it really is just the order parameter just flips from the plane to the z-axis, right? So the order parameter magnitude never vanishes, so it's not, of course, not a critical point. Okay, but if we pretend that we don't know anything, we just analyze the x and y order parameters and the z order parameter individually and look at them, we see behaviors very similar to what we did in the JQ model. So we see these step functions around delta equals 1. And if we analyze the crossing points and so on, they flow into delta equals 1. This is showing 1 minus delta here. And if we look at the order parameter squared, since we are a little bit below TC, we should get finite values as we do here. And also we can look at the slope 1 over nu. And now at a regular phase transition, 1 over nu should go to 3 in this case because it's a 3D classical model. And one of them appears to do, the other one doesn't quite appear to do. And we don't understand this fully yet, but it's not really a normal first order transition, so that's probably why. But the point here is that this behavior is very similar to what we see for this JQ model. But of course, in the JQ model, there's no obvious higher symmetry. We cannot look at the model and say, oh yeah, for this value of the coupling ratio, it has a higher symmetry. Well, maybe it does, but at least we have not been able to see that. So let me just put these graphs on the same slide so that you can see really how close they are. So here we have matched the colors of the points just to match the similar quantities. And you see it pretty much looks the same, except 1 over nu here it goes to around 3, here it goes to, well, whatever it is. We could actually have done the 04 Heisenberg model as well. We are going to do that as well. We already had an 03 code available, so we decided just to do that because we felt some urgency, right? So anyway, so it seems that we may have 04 symmetry here, meaning that the 03 AFM order may combine with the Z2 icing Placket order parameter and form a higher dimensional vector, similar to what would happen in some 04 model if you tune this anisotropy. So now we need to really detect and see if we have that 04 symmetry in some other way, not just this indirect evidence. So the AFM order parameter definitely has 03 symmetry. So if we want to detect 04, or it could also be SO4, actually we cannot distinguish between 04 and SO4, so I just wrote 04 here, but we are just testing for SO4, strictly speaking. So if we can check that this Placket order parameter and one component of the AFM order, if that develops O2 symmetry, then the whole thing should have 04 or SO4. So we look at this kind of distribution, which again we can do in our simulation. So now what we're doing, if we just imagine that we have an O4 sphere and we have points on the O4 sphere, so then we project down to 2 dimensions, and then we ask what's the density of points in that 2-dimensional plane. And you can easily see that that should be a constant density within a circle, which is the radius of the sphere. Okay, that's if we have a fixed radius. But now, if this scenario is correct, we should not really expect the magnitude of the vector to be fixed, because we have finite size. So that means even the magnitude of the order parameter will fluctuate quite a lot. So that's why we also simulated, this is trivial, right? Just pick points on an O4 sphere, but we sample it with a fluctuating radius where the standard deviation, so the radius is 1 and the standard deviation of the radius is given here. So if we have a fixed radius, we just get a circle. I just show one quadrant here. And then, of course, as we increase the fluctuations, this circle is smeared at the edges. So now let's see what we get for the JQ model, where on the x-axis now I plot mz, and on the y-axis I plot mp. And now I just go across the transition. So this is on the Placket singlet side. We get a blob up here, meaning we have a large MP and a small MZ, but there are large fluctuations because this is still close to the transition point. On the other side, so in the limit of infinite size, this would just be one point here, right? When the relative fluctuations go away as a function of system size. On the AFM side, we get this kind of distribution, which in the thermodynamic limit, based on this projection down, you can easily see that since this has three components, but we are looking at one component, it would actually go to a line, and here it's not a line because we are still close to the transition. But then we find some point where it looks, very much like one of these, right? So, and we can do statistical tests of this distribution, and we can actually not detect any deviation from the circular distribution based on the error bars we have. So it looks like indeed there's emergent O4 symmetry at the transition, and there's no conventional coexistence. The conventional coexistence now would be combining this one and that one, right? So we would have some high density here and high density here, and not at all a circular distribution. Okay, so right, so this is now based some ideas for this 2D model, which may carry over also to the Shastra-Sutherland model. So Corboz and Miller, they found a weak first order transition, so that's consistent with what we had. I forgot exactly what the discontinuity was there, but I think they said it was weak first order. So what we are interested in now is also the phase diagram as a function of temperature and this G. And again, we can sort of imagine that something similar will happen in the Shastra-Sutherland model and in the material as well. So here we break discrete symmetry, so we can have a finite TC, and this should actually be an Ising transition. And since I don't have much time, I cannot go into detail, but actually if we have emergent O4 symmetry, then this should actually go to zero TC should actually go to zero in some logarithmic way here, 1 over log G minus GC. That's known from works on ON models. So what we are interested in is basically to detect experimentally this kind of phase transition. So then the specific heat is a good thing to look at. So this is some very preliminary. This is far from being published. So you can see here that there's a broad peak here, but that actually has nothing to do with the transition. Then there's a very small peak here, which actually grows when we increase the system size. So this is for not such a big system size yet. So what is this broad peak here? Well, it's actually pretty easy to understand, because this phase transition has to do with ordering of singlets on the plaquettes, right? But on the plaquettes, you have lots of states. So before the singlets can order, you have to basically get rid of the higher states on the plaquettes. So there will be a lot of entropy lost also. So this is actually the specific heat divided by T. So if we integrate it, should get log 2. There will be a lot of entropy lost when we freeze out those higher states on the plaquette. So we get this very broad peak before the phase transition happens.
So
and
this temperature is measured in the unit of Q or J?
Yeah, good question. So I think it's in units of Q here. Yeah. Or sorry, actually it's not. It's in units of J plus. We keep J plus Q equals 1 basically. So it's in units of J plus Q. Okay, but in the material, of course, it should be 3-dimensional, right? So then we have to think, okay, if we have this emergent O4, by the way, maybe it's not completely O4. It could, of course, be that on some large length scale it's not O4, but I'm just talking about it as O4 now. And we find a first order transition, then it should probably be a line of first order transitions here. One could also imagine that there's some coexistence, but I think that's a little bit unlikely in this O4 scenario. And then, of course, the antiferromagnetic order will also have a finite TC. And it's interesting then to ask that if there's some, in the neighborhood of this first order end point here, well, we really don't know what happens here, but the point is in this wedge here, maybe there could be some remnant of this O4 symmetry, at least if the coupling between the layers is not too strong. So I think that would be interesting to look at experimentally in this material. Yeah.
Surely, if you come down in temperature,
Yeah.
right at that point, the antiferromagnetic correlation length will have this exponential increase in the function of temperature.
Right.
Losing the nil order.
Yeah, I think so, but it's not completely clear what will happen, if this is first order, and even.
So it should go above, come down, and it's weakly coupled.
Right. Yeah, it's weakly coupled, but of course, weakly coupled has a big effect in these layer systems. So this first order transition can go pretty high in temperature, I think even. Yeah. Anyway, that's things to be sorted out. So let me conclude this part of the talk. So we okay, I don't need to repeat much, but I should stress again that, of course, we cannot say for sure. Maybe it's actually more likely that there's some long length scale above which this O4 goes away, and we start to see more normal coexistence. But even having the coexistence on length scale, which must be hundreds of lattice sites, is quite intriguing, given that the transition is pretty strongly first order. So we were still checking that. And actually, at the same time, actually for once, we were the ones scooping somebody else, Nahum and Serna. They actually looked at some 3D classical loop models, at the same time as we did, and we sent them the papers, and they told us that unfortunately we scooped them. But then I said that was payback for them scooping us in the next part of my talk, which Senthil was also involved in. Anyway, so they looked at a model which is also related to deconfined criticality. They deformed the initially Z4 VBS type state, and so that's similar to what we did with the JQ model, and they also find a near O4 symmetry. So they really say that they don't find perfect O4 symmetry. They see some weak violation of O4. So what we want to do actually in the future, yeah. Also first order, yeah. I mean, there could even be, well, okay, let me comment on that now, because there could be a tricritical point, right? So now we have these Q plaquettes here, but we could also just have two different values of Q, so QA and QB on these and the other plaquettes. And then you can ask, is there some value of QB over QA where the transition becomes continuous? And is that then a point with higher symmetry? Of course, when QA goes to QB, it goes back to the normal JQ models, the symmetries change and so on. So we are looking at that now. I don't want to say anything about it at this point. And we are also looking at, with the experiments in mind, we are looking at 3D couplings. And actually, for once, I'm really collaborating with experimentalists now, because at IOP, there are people doing all kinds of experiments, including they have a very strong high-pressure group, and they also have people making material. So the material has been made, and we already have initial specific heat results to detect this icing transition, and I think I should not tell you what the results are, other than it looks quite nice. So stay tuned about that.
So it sounds like this QB model, where you put it on the empty sites, is closer to the what's seen in J1, J2.
Yeah, I think so. Yeah.
Could be interesting.
Yeah. Yeah, exactly. We definitely look. Yeah, so maybe I can even take a few questions about this part before moving on.
So the simple example that you gave is XY to icing order going through a spin flow transition. So there it's then to say generically you have two order parameters XY and icing.
Yeah.
The generic transition will not go through the spin flow.
Right. Yeah. I know. We are looking at there's a lot of literature like that. Yeah. So if you just do some model that you mean if you don't have explicit symmetry, right?
Exactly.
Yeah. So then. Yeah. So you can ask classically, even if you have, you know, ON1 and you have ON2, you know, let's say here is N1 and here N2. So then you can ask, is there a point in between? Okay, so now maybe the phase diagram will look more like this. So here it's N1, N2, and then you can ask, is this ON1 plus N2? And that's known to be the case only if N1 equals N2 equals 1, right? Otherwise, it's not the case. But that's within the Landau scenario, so, you know, maybe something could be different, I don't know.
So this is unusual.
Right, yeah, it's unusual.
You're passing near some critical point.
Right.
Enhance your O4, it's not quite O4, and then you get a...
Right.
Because this tight critical.
Right, yeah, so we're looking for that, so, yeah.
Maybe this,
That is the
that's the tight critical.
Right.
It's not
Right.
tight.
So Tenka, did you have a question?
Oh, just a quick comment. I mean, you mentioned several times about SO4, O4. I think just, if it's SO4, it should be O4.
Uh-huh,
Because that is Z2 reflection. You
Right.
actually flip your Placket order is precisely Z2 subgroup of the O4, which is not in SO4.
all right, so it change, yeah, so if I flip along a diagonal, you say here, I change,
Exactly.
yeah.
That's
Right.
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 The Placket.
So you say that there's a reflection operator you can define, right?
Which actually is a Z2 subgroup of
Right, right.
which is not in SO4.
Yeah, no, I think you're right, yeah, it should, yeah. Yeah, actually initially we talked about it like SO4, but then, yeah, we realized that there could be, it should actually be, yeah,
So this XXZ-JQ model,
right,
which I mean, so when you go to this delta equals 0 limit, the XY
Yeah.
limit, there too is a first order.
that's right.
Is there a similar O4?
Yeah, good point. Yeah, so we could have looked at that in our recent work, but we didn't. So we will do now. Exactly. Okay, so let me. Yeah. Okay, one more question.
So, you know, if by any chance at the transition you have an actual symmetry that is O4, maybe I think it might be a good idea to look at EV spectra, because there the multiplet structure of O4 will show up.
Yeah,
high energy.
that's good point. Except that maybe, you know, the systems we can do then are not so big, and yeah, but yeah, we want to definitely look at that.
Because if it's not emergent, right, maybe you're close to a model that actually has the symmetry.
Right.
Like in this example you put, in which you really have SU2.
Right.
Multiplet structure.
Right.
You should be able to see that on top.
Yeah, exactly. So if there really is a symmetry, you should be able. Yeah, exactly. No, it could be that for some reason there's an exact symmetry. Who knows? Yeah. Okay, so I think I don't have much time for the next topic, but I will just say something quickly. But how much time can I take away from the alcohol? Will the alcohol wait for us, or will it evaporate? Right. Okay, so this is about the random singlet phase that we believe we get when we make this JQ model, the normal JQ model disordered. So this is done with my Chinese collaborators from various places. Okay, so there's some theoretical motivations for this. Just say, okay, this deconfined critical point, you know, what happens to it in the presence of disorder. But there's also an experimental motivation, because there are lots of spin liquids with disorder, and actually maybe you can actually understand those as disordered valence bond solids. That has been also proposed by Sentil and collaborators quite recently. So what we will do is, what we have done is show quantum Monte Carlo evidence for the so-called random singlet phase, which is a disordered valence bond solid, basically, which has some critical magnetic properties. So we have characterized those, and this is in that preprint. So basically, it goes back to this story, what is a spin-on in the context of a valence bond solid. So this is the picture of Levin and Sentil, where you have a meeting point of the four realizations of the columnar VBS, and then you have to have an unpaired spin-on in the middle. So we will use colors just denote these angles of the VBS order. And then, of course, the point is that with fluctuations and so on, there's really a continuous change of angle as you go around here. So now there's the Imre-Mar argument. If you have a discrete symmetry breaking and you put this order in 1 and 2 dimensions, we know that you cannot have an infinite long-range order anymore. You will break up the system into domains. So in the case of the valence bond solid, and because of this picture of spin-ons here, you will get the domains that are actually, well, you can get some trivial domains like this. So the domains have to have a phase shift of pi over 2. So, for example, red and blue can be next to each other. But you can also form more non-trivial domains. Here is the simplest one, where you have 2 of these spin-ons that connect to each other in this way. And because of the structure of this domain wall, the pi over 2 domain wall is the elementary one, you will actually have to have all these phases coming together when you have two spin-ons like that. And you can think of spin-ons and anti-spin-ons. So this is just the VBS, but then you can say, okay, so the VBS will be destroyed. But now you have these spin-ons that in the disordered system will localize because they will form at some energetically favorable places. What kind of magnetic properties will form? And in 1D, we know that the random singlet phase forms generically. The Heisenberg chain with arbitrarily weak disorder will give the random singlet state, which is corresponds to an infinite randomness fixed point. The state has mean correlations decaying like as a power law, and there are interesting dynamic properties and whatnot. So in 2D, people have been looking for that kind of state in SU2 systems for a long time. It has been found in transverse field Ising models and things like that, but not really in SU2 spin systems. So what we seem to find is something that looks like a random singlet state. But then there's this paper by Kim-Chi, Nahum, and Senthil, who say that on the square lattice we should actually expect weak antiferromagnetic order. And Senthil can, of course, object if I misrepresent their work.
Yeah, no, I should say that we don't know.
Right, yeah. Okay, of course you...
So we didn't make a strong...
Yeah, because what you did, you said H equals ... we cannot exclude anything, right? No, just joking. But okay, but you said the most likely scenario is that you form weak antiferromagnetic order, but you cannot exclude other things. Yeah. Anyway, so let me talk about a simpler case where this weak antiferromagnetic order appears, and I somehow have to try to do things fast. But okay, so if we take a gapped system, like a manually dimerized model like that, and take away some sites, then there will be some leftover dangling spins, and those will order antiferromagnetically because there's no frustration. So, they will actually form like a subsystem of AFM order. And just as a sort of point of comparison, we did calculations for this system too. So here now again we use bin accumulants. And in the clean system, there's a phase transition at this ratio between the Nell order and the gapped phase. And here these bin accumulants don't really cross each other. The crossing points flow to larger and larger coupling. So this is at some weak dilution, 1 hole per 32 spins. I should have said that here. So eventually, actually, for a fixed value of J2, the bin accumulant, okay, it first decays, but then it turns up and starts to go to 1, which reflects this weak order. So then one could say, okay, the spin-ons that are in this disordered JQ model, for example, they will do something similar. They will also form weak AFM order. So is that really the fate of those spin-ons? That's the question. So Senthil et al. Did not exclude that something else happens, but they said the most likely scenario is that happens. But then the main part of their paper was devoted to the triangular lattice model, which of course is frustrated. And then they argue that at least up to some length scale, there's the random singlet state, but it may eventually actually be unstable to a spin glass, if I understood Senthil correctly. So our conclusion is that we actually have a random singlet state. Well, I should, of course, say that we cannot also completely exclude that eventually we get some very weak AFM order, but we have some arguments against that, and the numerics for the transition in particular looks so nice that somehow we believe that that happens. Okay, so we take the JQ model, we try dilution, but let me not talk about that here because that indeed shows this more trivial behavior. But when we do random couplings, we get this kind of phase diagram. So when we have dilution, we basically destroy the transition. We just get some crossovers. But here we believe that we have an actual phase transition. So here this should represent the strength of the disorder in some sense. And we have not studied that systematically. We have just picked a few cases, but based on those, we basically can deduce that we should have that kind of phase diagram. So let's see what should, okay, at least maybe I can show you some pictures. So this is one realization of the disorder, and these colors are coding the bond strengths that we measure in the simulations. And you can see that we have these domains, and you can also see many places of these spin-ons. So here is maybe the clearest case. You see that all four phases go together. And then we can also measure some other properties. For example, we can measure a local susceptibility in the same configuration. So this is just the local response to a magnetic field, a local magnetic field. And you can actually correlate specifically, if you go deep inside the domains here, you will see very dark regions here. And otherwise, you will see bright things. And those bright things, which means high susceptibility, corresponds to where the spin-ons are localized. But it's not only there, but also in the domain walls, the response is larger. So we believe that that's a key ingredient to understand this random singlet phase, that actually these domain walls mediate the interactions between the spin-ons. Okay, so firstly, the spin-ons are created in pairs, and secondly, the spin-ons interact more strongly than you would expect, pairwise, because of this role of the domain walls as having smaller gaps, if you will. And we believe that avoids this terrible fate of AFM ordering, and instead we get a state which has power law magnetic correlations. And I don't...
correlation between the direction of this domain wall and the kind of domain wall you're getting?
Sorry, I didn't... What?
So are all of these domain walls equally gapless?
No, okay, no, it's very complicated, of course. And we have studied some clean domain walls as well, where we can clearly see that the gap is smaller in the domain wall than in the bulk. But of course, in the disordered system, we cannot really define easily the local gap. In some sense, you could define it from here, but you see there's just some higher response on the domain wall.
Not only that, the domain walls which doesn't have a gap are not really these ones. They're not these default.
Exactly. So these are the gapless. Yeah. So the gap domain walls are the pi domain walls, right?
They're like a bound state of two of them.
Right. Yeah. So there's a lot to discuss about domain walls as well, but in the interest of time, let me just figure out what I should show you to convince you that we have. So basically, we can look at the phase transition. I think that's actually our strongest evidence for this phase, that we actually see a very clear phase transition out of the null state. So again, we can look at the bin accumulants, how they flow, and analyze the crossing points. And now we have the dimer order parameters, so if we, and the magnetic one. So if we look at the dimer one, so this is just for some random J situation, the crossing points just drift. And eventually, this Q star, which is the crossing point between L and 2L, goes up to infinity. That just means that we always break up the system into domains. The order goes away. But the magnetic cumulant the crossing points seem to converge. So that's those red dots here. They seem to converge. And what is the black dot here? Well, this black dot is something that I don't really have time to discuss now, but let me just put up this slide. It's basically in the valence bond basis we can look at not only the ground state, which is as a singlet, but we can also look at the spin 1 state. You can think of the spin 1 state as containing 2 spin-ons. So in the valence bond solid, the spin-ons will be small, and actually a spin-on, when we take basically what we are sampling in the simulation is the normalization, and that's broken up into many contributions that can be represented by these so-called transition graphs. And since the states are basically non-orthogonal, a single spin-on will actually be a string in that representation. So in a clean VBS, which this actually is, even if it doesn't quite look like it, these are short. In an antiferromagnet, these strings are very long, actually of the size of the system volume. And then we find, and this is just an empirical observation, I guess, that the fraction, the string fraction, meaning what fraction of the system is covered by strings on average, goes like 1/L. So that is somehow seen very clearly, and we don't really have a good explanation why, but we can also just say, okay, if that's the case, if we do L times lambda, we should also see crossings, which we do, and those crossing points flow also to the same point. So we have somehow 2 different evidence for the critical point, and this is in two different cases, random J. It's actually a bimodal distribution of J and also bimodal of Q. So we can find a phase transition there. Then we other properties that we can look at. Okay, I mentioned already that the spin correlations decay as a power law. Actually, they seem to decay as 1/r². So these are 3 different cases. The spin correlation at the longest distance as a function of the system size seems to show the same decay in all cases, and it's very close to 1/r². The dimer correlations, bond-bond correlations are very noisy, but they seem to go like 1/r⁴, and both these are actually the same as what the 1D random singlet state does, which I don't know why it should be. Okay, for experiments, probably the most useful quantity is the magnetic susceptibility, and from that you can actually extract the dynamic exponent if we believe that we can apply standard quantum-critical scaling arguments. Then the uniform susceptibility as a function of the temperature should behave like that, where D is the dimensionality, Z is the dynamic exponent, and that is in the thermodynamic limit, so we have to go to big enough system size. So now I showed you one case where we extracted the critical point to be around 1.2. So let's now look at the temperature dependent susceptibility exactly at that point. And this is what's shown here for different system sizes. So we can study it for many temperatures and sizes, but we want to look at it where there's no size dependence anymore, so that we are in the thermodynamic limit. And you can see that this is extremely flat here over 1.5 decade in the temperature. So that corresponds to Z equals D here. So the dynamic exponent seems to be 2 at the phase boundary, and this is also seen at in other cases where we looked. But if we go further inside the phase, then you can see that we see a divergence, and we actually fit this to a power law in T, but there's a correction that allows us to fit it a little bit better, just a constant. And that corresponds to Z being larger than 2. So we believe that the dynamic exponent is exactly 2 at the phase boundary, and then it grows and varies continuously inside the random singlet phase. Okay, let me quickly say something about experiments, I guess maybe 1 minute. So, this is also what the Sentil et al. Basically focused on, that actually many spin liquid candidates actually have a lot of disorder, and it may be in the form of random couplings, and maybe then they could actually be random singlet states, which you can say is a type of spin liquid, I guess, but maybe not the kind people had in mind. So there's this recent class of materials which is very nice, shown here. Basically, it's a layered system but there's something within the plaquettes which actually will determine what the couplings are. So if you have tellurium here, it's basically J1 dominated, and if you have tungsten here, it's J2 dominated. And now those have been characterized, and indeed this is a very nice Snell state, and this is a very nice stripe antiferromagnetic state. And now they can actually mix these, because these tellurium and tungsten, they can actually be replaced by each other without changing the crystal structure much at all. So one can actually look at mixtures. So there's this very recent paper where they looked at a 50-50% mixture. So these are the clean limits here, and then they see this kind of behavior here. And they actually said that this tail here is just a Curie tail because there's some magnetic impurities, but I'm just wondering, could this just be a sign of random singlet state? Because this is also a situation where you mix these, that you could imagine that you actually get the random singlet state. And they actually didn't really analyze these, so I don't know what the power law is and so on. Actually, there's a more recent paper where they have many concentrations here, and you can actually clearly see that this tail evolves as a function of this X here. Okay, so this is pretty much what I wanted to say. Let's see. Well, so I think what we would like to believe is that this random singlet phase is universal, so it could be the same as in the frustrated systems that Sentil et al. Looked at. But now we can actually really calculate some properties with QMC, as I showed you, and we can do comparisons with experiments, at least in terms of things like, okay, we predict varying Z, so then you should not expect some specific power laws. You can expect different power laws in different cases. So we are working on further characterizations of this phase, and we also have some other models in which we can realize it. Okay, thank you very much. Yep.
We are a bit late, so I think we should just take short questions and
Right.
have a drink outside and continue the discussion.
Okay, sorry. So theoretically, what is the entanglement entropy of the random singlet phase in 2D?
Right, yes, I don't know. Of course, in 1D it's well known what it is. In 2D, I suspect nobody knows, right? But it's definitely something we should also calculate, I think, but we have not. Yeah.
There's the spin, this network of dangling spins
Right.
of the square lattice.
Right.
As I presume, there's an effective model
Right.
for that, which
Yeah.
has this lattice type disorder,
Uh-huh.
so it's J out prime times epsilon out prime.
Uh-huh.
So that's why it's unfrustrated.
Right.
But that's an effective model for this dangling spin.
Yeah.
Now that model, I presume, doesn't have a sign problem because all the signs.
Yeah, that's right.
So that, if you simulate that.
Yeah, we should. But then I think it's really important to take into account the correlations, right? Because I think I said it here somewhere, maybe not. So I mean, we don't have just a random collection of moments. I mean, they are strongly correlated because they are formed pairwise, and then the interaction also is probably not what you would naively expect. So I think one could start from that, but maybe build in these other features that we are finding.
So maybe that you get lucky, and as you increase the width of that distribution of J,
Right.
that
Right.
there is a transition.
Right.
Of
Yeah.
maybe
One could look at.
shape of the distribution.
Right. Yeah. Yeah. I think you need to take into account this pairwise formation of these. But I guess that's just a distribution, if you will. Yeah. Yeah.
If you start from a Q2 model like the one we analyzed, would you expect then that these sort of spin-outs which are attached to the main walls to be different because
Yeah, good question. Yeah, I was actually thinking about doing that. Yeah, it could be different, but I haven't thought about it enough to know what it would do. But
properties on
Right.
top of this network
Right.
would be very
Right.
different.
Also, the previous model I talked about, one could also do it there, right? Yeah. Anyway, we can talk about that. I think that our chairman wants us to stop now. Thank you.
Thanks for that.